All right, so let's talk about line driving. So Ken Gailey had one of the most profound ideas of anybody I've ever known while he was my postdoc. And he was telling me about this one time when in the car, I kind of have this idea, you know, and it was a brilliant idea. This idea that we're used to electron scattering. Electrons scatter photons. As soon as you take that electron and you put it into a bound state, the cross-section goes up by 10 to the 8. It's the ratio of the lifetime of the atom to the photon frequency. Now, only have a few atoms that are actually in bound states in our ionized atmosphere, so you have to correct for the abundances, but you end up with this quality of the resonance, Q, averaged over all the ionization. Q bar tells you that line opacity is much more powerful than electrons. And that's why we can reach the Eddington limit, we can reach winds even when we're 1,000th of the Eddington limit, because this number Q bar is on the order of 1,000. And again, that's Ken's great insight. Now, of course, what ends up happening is that you don't propel everything with 1,000 times like a scattering. You end up self-saturating the lines, and then they have to desaturate in order to get acceleration. And so you get a force in general that goes like the velocity gradient. Anyway, there's Ken mansplaining to Chris about something. I don't know what it is. Chris is listening very attentively. Chris is always too polite to tell you, I already know all this. All right, so what happens in this idea about line driving? Well, of course, you go like the velocity gradient because you desaturate yourself as you accelerate. But when I was a postdoc at Harvard, George Rybicki was right across used to come to these coffee breaks. And I used to chat with him about stuff because I was doing my thesis was on solar wind, and I was publishing that with George Withrow. And then Leon Lucy comes and gives a talk about so-called black troughs, where in order to understand the saturated central parts of P Cygni's strong lines, you have to basically assume a backscattering effect. And that comes from multiple non-monotonic, a wind that's very non-monotonic. I mean, I could put graphs up about it. So his conclusion is that these winds are very non-monotonic, they're very turbulent. And so George and I said, George, I'd really kind of like to try to figure out how that works, you know? And, but I'm looking at these papers and it's, you know, it's like, so I had to make it simple enough that even I could understand it. So what I said is, what if you had a wind that was moving at a constant gradient, and then all of a sudden, you suddenly switch the gradient? How would the force respond? Would it just respond like a step function, the way CAK theory tells you? No, it doesn't, because there's a certain finite thickness to the absorption layer, which is set by the Sobolev lane. And so in this region, oops, sorry about that. In this region here, the increase in velocity, the increase in force is proportional to the velocity difference, not to the velocity gradient. Well, when you have velocity difference, the perturbation of the velocity difference, you have a very different situation. Here's the standard Abbott waves that we heard a lot about earlier. When you perturb the thing and it's proportional to the velocity gradient, you get a wave that propagates back inward toward the star, but it's stable because as we heard earlier, the force and the velocity have a 90 degrees phase difference, so there's no work on it. But here, if it's proportional, the thing doesn't propagate, it just grows in place. And this is then, to bridge these two limits, George Rybicki and I came up with this bridging law, where this bridging length is of the order of the Sobolev length, the velocity divided by the velocity gradient. Now, okay, so Leon Lucy, who's going to come up several times in this discussion, Leon was the referee on this paper. It was, you know, we were really proud of this paper. Bridging law, 2 different domains, you know, unified. That's pretty heady stuff for a postdoc, you know? And Leon just said, oh, you guys have forgotten a really key effect. You know, I find that if you put scattering in, this instability goes away. And now the way let's try to understand the difference between absorption and scattering. And Achim talked about this a fair amount in his talk. But we always have different ways of explaining it. Here's the basic idea of absorption. The wind accelerates, and then photons coming on here, and then the amount of photons that get absorbed per unit length. This is the thermal width of the line that's being Doppler shifted. And the photons just come in, and it's the number of photons velocity gradient. But another way to look at it is to go in the frame of the photons they're getting. Instead of the photons being fixed in frequency, the photons get redshifted. And they get redshifted into the line. They're on the blue side of the line. Then they have to, scatter their way through the line. Now, if Lex Kappa were here, I would say, how many times does it have to scatter? It has to scatter many, 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 many times because it's set by the Sobolev optical depth. But by the time it gets out on the other side, it's forgotten which way it came from. So it goes out isotropically in two different directions, for after symmetry. And so the net recoil from the scattered photons is 0. And so that's why everybody uses CAK theory. They don't put the scattering in. So here's how you can think about it. Here's the absorption profile. Here's the intensity coming up from below. It's absorbed. There's the direct force and the integral of the profile. And then here's the extra force you have if you perturb it to high velocity. That's proportional to velocity. That's the line-Deshadowing instability. And then here's the fact that in a smooth flow, that forward and Achim had a sort of similar way to show this. But now you have the force on a positive force here and negative force there, and they cancel. The diffuse force is 0. But now if you Doppler shift out of the shadow in the co-moving frame, if you're not in the co-moving frame, you get a bigger negative force here than you do a positive, and that's a drag effect. That's what we call the Lucy line drag. All right, so Lucy said, you're all wrong. And then once we understood what he's talking about, we did our own paper. Now, Lucy held up our paper in 1984 till he published his own paper saying we're all full of baloney. And I don't know if I would use that word. If it were politer to use the right word, I would say. But anyway, the point is that as a referee, he held up this paper and published a paper right after it. So in 1985, I did a full analysis. Many of the approximations that Lucy had made were not valid. And I let him have it between the eyes. I mean, I basically, told him, no, this is not true, that the instability is canceled. And we went through this. And there are lots of things that we learned from this analysis, including the fact that now there are new wave modes from the perturbed source function and so forth, some of the things that Joe was talking about earlier. So the bottom line is that the instability would be weakened somewhat, especially near the surface of the star, but in the outer wind, it's still very, very unstable. So we decided to proceed with a pure absorption model for the nonlinear. Now here's another example. John Castor and George Rybicki are like gods, right? George Rybicki is one of the smartest radiative transfer persons. John Castor, there's the book by Dmitry Mihalis that said John Castor knows more radiation hydrodynamics than anybody I know. Dmitry Mihalis said that. But when we were getting ready to write this paper, when I was writing this paper, they were nervous about submitting this paper. What would Leon say? And I said, I don't give what Leon says. We have made big progress. And I go, so it was Dave Abbott was the referee on the paper, and it was his last referee because he gave up science. He went to teach grammar school. This is in 1988. And he said, this is going to be a paradigm shift. He predicted that. This paper now has 800 citations, my most cited paper. And yeah, what can I say? This is when I just transitioned from a postdoc at Harvard to basically in San Diego. And that's a whole nother story. I had to negotiate to continue to be able to work on radiation-driven winds. All right, so then I had this, right before the Trieste meeting in 1991, I had this epiphany of how to put scattering in. And something called the smooth source function method. John showed some of the equations behind it. But the basic idea was that you could recycle the pure absorption optical depth by just turning the photons backwards and then take the difference in them, the escape probabilities, and you could get a force that included with almost no increase in computational costs, you can include the line drag. And what you find out is what it does is it stabilizes the base just like Leon said it would, but the wind was still very unstable in the outer part. And it even self-excites itself because now it has a way for photons to communicate back upstream by using the scattering. And the other thing it did is it got rid of this other problem that Joe alluded to, this nodal topology that made the wind intrinsically unstable, unless you went through the steeper slope solution here. And you see the original pure absorption model is much steeper than CAK. And then the other thing, of course, is that the shocks are reverse shocks in the OCR model. All right, so Joe comes along and Joe had read my papers. You know, how many people actually carefully read your papers? And Joe recognized that there was now a forward mode instead of the reverse mode, the inverse mode that would grow into reverse shocks. There was a forward mode that was unstable. And he said, we should include that. That involved the gradient of the source function. So we couldn't use the smooth source function. We had to go to the next highest level. And so that is called the escape integral source function. And the escape integral source function, I don't have it showing it here. It turns out it's unstable, but as soon as you get to amplitudes of about a thermal speed, it stops growing. Kind of like what Carl Wood claimed about the original LDI. But to our surprise, this nice correction that occurs in the smooth source function method, here's the direct force. There, the direct force is almost like CAK when you add it to the diffuse force. It gives you this total force, which is almost like the Sobolev model in the sonic region. And if now you put in this, you get the source function dip that Joe talked about in his talk. And now there's this weird, almost like a step function in the driving. And this now calls into question the launching of the stellar winds. All right. The other thing is, everybody said, oh, but Abbott waves, they propagate in faster than sound. But you saw the stuff that Achim did. They don't carry any information in the pure absorption model. So what I decided to do was take a model with 3 different approximations for the driving, run it forward, and then go back to the source with fixed time steps, go back to the source and edit one grid point by 1 kilometer a second. And then it ran the exact same simulation with the same time steps, and then took a difference between the 2 files. This is like what we call a Green's function, right? It's when you have a point source, how does the wind respond globally to a point perturbation? It's a numerical Green's function. And here's what you find. First of all, the density and velocity are antiphase when it's white. So these are all antiphase, they're all inward propagating structures. In the frame of the star, the stuff hardly moves. In the frame of the wind, it actually propagates inward. That's what Abbott predicted, okay? But now, here you put the smooth source function. Now it propagates inward and a little bit outward, okay? And because now you have scattering carrying information in all directions. So you notice that the front here is very similar to Sobolev, similar to Abbott. And then you put the EISF, you find that there's positive density and velocity. That means you could potentially get forward shocks, but they saturate. I'm very proud of this graph. 99% of the people, or 99.9% of the people have no clue what's going on here, but this is a beautiful, if you want to ask yourself about information propagation, this is your baby. Okay, so as I said, there was this nodal topology that made the winds very unstable, but when you put the smooth source function method in, it stabilized the base and everything was all happy. Then John comes along and we start playing around with the smooth source function method. And as Joe already alluded, if you just change things a little bit, put in limb darkening or something like that, or you change this scattering source function, there comes the nodal topology again with its intrinsic instability. The wind does not have this nice smooth initiation. All right. So meanwhile, on this paper, Leon was the referee again. And here is his report. Oh, sorry about that. He was very, very angry at me for things that I said in a public meeting in 1997 at ESO. I remember being publicly lambasted by a walkie at a conference in 1987 and I was advocating for CAK and a chilling effect on the field for 20 years. This is a man who invented SPH. This is a man who developed a Lucy deconvolution algorithm to correct for the Space Telescope spherical aberration. This is a man who invented line driving, okay? And here I was a lowly postdoc, but he treated students and other people sometimes very badly. And here's this young postdoc who's been his nemesis, you know, and I apparently cast a pall on, lambasted, or you call it a chilling effect. Now, what I want to say about this is Leon was a great scientist, but imagine how much better he could have been if he listened to other people and exchanged ideas and took their point of view into account instead of staying consistent. He criticizes me for changing my position over the years. But that's what you should do as a scientist. You should always be going with the latest new information you have. But Leon was still stuck in his one-sided derivative, you know? And so in other words, even great scientists can have blind spots. And what we should endeavor to do is to emulate the greatness of somebody like Leon Lucy without emulating his flaws. So I wanted to say, here's the Wikipedia page for Leon. Notice he mentions the smooth particle hydro. It mentions his there's not a word mentioned here about line driving. But it shows you how important we are to the rest of the community, right? Anyway, Leon died in, 1938 to 2018. He had more influence on me than I would ever know. And may he rest in peace. All right, so now we get back to John and this 2D LDI simulation that we did. The structure starts out as shells, but then as John showed earlier, it all breaks up and you get the structure. The base is still very unstable because it's a smooth source function method. And so what happens to this? This is, John already talked about this. You can characterize this by looking at this correlations between, if the wind were smooth, this would be a delta function. But because it's not smooth, it has a broadening. And again, it follows, what's the word for it, John? Turbulence. Anyway, it follows statistical distribution, but you can fit it very well with the exponential power law. Log normal turbulence, yeah. Anyway, there's John and me, one of the previous visits to Leuven, our treasure from going on the tour at Stella. Now, I should mention, my wife and I have been to Leuven several times. Last time we were here was pre-COVID, and we were in this hotel. It was incredibly hot that summer, and we're drinking a lot of beer out in the plaza. And Susie says, our next dog should be named Stella. And I said, okay, but it's going to be Stella Win. Okay, so now let's go forward to Steve Cranmer, another manna from heaven, you know. I mean, here I am, a young assistant professor at Delaware, and I get this word that there's this student named Steve Cranmer who wants to apply to grad school, and he came from Ohio State. I spent a year at Ohio State on my transition to Colorado after I was living in Germany, and I wrote George Collins. Anybody might know who George Collins was. He's a pretty famous person and very, very self-assured, I guess I would say. But anyway, I said to him, "What do you think of Steve Cranmer?" And he says to me very pointedly, "Steve Cranmer was the best graduate student ever to come through Ohio State." Well, apparently that included me. So anyway, Steve shows up, and one of the things we did was this model for the discrete absorption components using spots, and Nicole already did a quite extensive summary of this review. But the key thing I want you to notice is that the wind is basically, what you do is you put a spot, and at some point the wind, instead of being accelerated, shifts to a slow acceleration, to a kind of a flat, to a kind of a coasting. Now that coasting has a lot smaller velocity gradient than the wind, and therefore when you look at the spectrum, there's lots of absorption there, and that's the origin of the discrete absorption components. And it goes a lot to this idea that if you overload the wind, you will basically switch from a positive acceleration. So Ken Gailey, again, has these beautiful ways of thinking about it. And he came up with this idea, what we call the seagull diagram. The seagull diagram says, let's look at the equation of motion. Let's imagine we could take the acceleration divided by gravity, because that's after what the acceleration has to compete against. And let's write our equation of motion. And gravity is now 1, because you normalize everything by gravity. This is the inertia, and this is radiative driving. Oh, I'm sorry, I got a 2 there. That should be alpha. Yeah, so I'm sorry, that should be an alpha. I think in this case, yeah, well, anyway, it should be an alpha. It should be 1/2, not 2. And anyway, so now if you plot, there's the 1 plus, there's the inertia plus gravity, and here's the CW to the alpha, and C is depending on the mass loss rate and the flux of radiation. And normally what happens is the hardest place to drive a wind is right at the surface, because you have this so-called finite disk correction effect. And so what happens is you have the CAK, the so-called critical function. It's just one solution right there. That's the catastrophic inclined solution. And what happens is that the wind becomes easier to drive. And so you get 2 solutions, one up here and then one down here. And normally the wind takes the accelerating solution, but Joe mentioned how you could also have this solution. But what happens if you put a spot on the spot? You drive so much mass that then when the spot shrinks, now it can't be sustained. So what does it do? It switches to the backup solution it has, which is a negative acceleration back here. This is the origin. This is the physical origin of the plateaus. This is the physical origin of how a spot model can give you discrete absorption components. And I think it has a lot to do with the stuff that you talked about in your presentation this morning. And we can talk about that. All right. So let's now move on to disks. This is Van Hub. How's it go? Van Hub, right? I first gave a talk about this in